How's it going? Today I want to talk about section 7.4, products and quotients of complex numbers, basically multiplying and dividing complex numbers. So we may see something like this, and you treat it exactly the way you think you should. And foiling something like this is exactly like foiling it with x's, where we take that 3, we foil it through, and we get 15. 3 times negative 4i is going to be negative 12i. And then we take the 2i through. 2i times 5 is going to be 10i. And then 2i times negative 4i is going to be negative 8i squared. So it foils exactly the way you think it should. The one difference here is when you go to combine like terms. Yeah, just like before, we have our middle terms, which we're going to be able to combine, which is negative 12i and positive 10i, which makes negative 2i. The difference is this part right here, because that is actually a real number. Because remember, I squared, like we talked about last section, is equal to negative 1. So this is actually negative 8 times negative 1, or a positive 8, okay? So this can actually be combined with that first real part, the 15, to make 23. So the only real difference here between multiplying complex numbers and multiplying like binomials with 2x instead of 2i is if they were x's, we would only combine those two middle terms. But because I squared is actually a real number, it's equal to negative 1, that just changes that to a positive 8 instead of a negative 8i squared. Make sense? Take something like this. Now, some people would think, because we do have a rule with radicals, that the square root of x times the square root of y is equal to the square root of xy, right? Like that is a rule that we've established as fact. And they would think because of this rule that we could do something like the square root of negative 4 times the square root of negative 16 is equal to the square root of negative 4 times negative 16, where the negatives would cancel. But you're actually not allowed to do that. That rule actually only applies if x and y are greater than or equal to 0, right? So if it's less than 0, that rule actually doesn't apply. So the way we actually have to treat this is we have to turn these into imaginary numbers. So this is actually going to equal, the square root of 4 is 2, so that's going to be 2i. And then we have to simplify this, which would be the square root of 16 is 4i. Then we multiply. 2 times 4 is 8. I times I is I squared. And then again, we use that rule, I squared is equal to negative 1. So this would actually equal negative 8. Okay? So we can't actually use that rule. That rule does not apply for imaginary numbers like these. So you have to simplify them first, then multiply. Okay? Let's try another example here where we multiply. Okay? 5 minus 3i, 5 plus 3i. Kind of looks like a difference of difference of two squares kind of thing. And something interesting is actually going to happen here. Sometimes we multiply imaginary numbers and we don't end up with an imaginary number. And the reason is when we FOIL this out, we get 5 times 5 is 25. We get a positive 15i. Then we get a negative 15i. And then again, we get negative 9i squared. These two parts cancel each other out. And then again, because I squared is equal to negative 1, that's actually going to equal a positive 9. The final answer here is just 34. So we can multiply two imaginary numbers and get back to a real number. Okay? And that actually leads me into my next term that we have to talk about, which is conjugate. Okay? And what a conjugate is anything in the form of a plus bi has a conjugate of a minus bi. So 3 plus 5i and 3 minus 5i, those are what we call conjugates. Negative 2 plus 3i and negative 2 minus 3i. Those are going to be conjugates of each other. And basically, what happens is when you multiply a plus bi times a minus bi, the resulting answer is going to be a real number, okay? So, because what ends up happening is you get a squared minus b squared, and because it's an I, you get squared, it gets back to a positive, and you end up with a real number. So conjugates are actually really easy to find. All you do is change the sign of the second term. The first term stays whatever it is. And that becomes important when we start talking about division or even simple concepts like finding the reciprocal. If I have to find the reciprocal of 3 minus I, which would be exactly what you think, 1 over 3 minus I. Now, when we start doing division with imaginary numbers, it's actually a lot like dividing with radicals. And what I mean is something like 2 over the square root of 3, right? Where, there's not actually a whole lot we can do to divide those, but we do simplify them. And we simplified this by rationalizing that denominator, making that denominator a real number, right? Remember, we multiply by a big fat 1, square root of 3 over square root of 3, right? That's where we'd get 2 root 3 over 3. And the whole goal here is actually to rationalize that denominator, make that denominator a rational number. Well, the idea here with imaginary numbers is kind of the same thing. We don't want an imaginary number in our denominator. So what I call it realize the denominator. So we're going to make that denominator a real number, okay? Kind of a fun way to say it. They realize it. So the way we do that is we're going to multiply by what we call the conjugate. So the conjugate of 3 minus I would be 3 plus I. Of course, whatever we do to the denominator, we also have to do to the numerator, right? So basically, it's kind of the same concept here as when we dealt with radicals. Now we're just going to take that denominator, we want to make that a real number. So when we multiply straight across, 1 times anything is just that, 3 plus I. The denominator, we FOIL. 3 times 3 is 9. Remember, the middle terms are going to cancel because you'd have a positive 3i, and then you have a negative 3i. And then negative I times I is going to be negative I squared. So that will simplify to 3 plus I over, remember that I squared is negative 1, so that's the same thing as 9 minus a negative 1, or 9 plus 1, or 10. All right, so that's how you actually do division. And that's going to be the same, if we have to divide something that looks like this. The whole idea here is just to realize that denominator, make that denominator a real number, okay? So we figure out what the conjugate of 3 plus 2i is, which would be 3 minus 2i. And again, whatever we do to the bottom, we do to the top, right? And then again, we just FOIL. The denominator, we're going to get 3 times 3 is 9. 3 minus 2i is negative 6i. Then you'll have a positive 6i, and then you'll have a negative 4i squared, which will again simplify to that's the same thing as positive 4. So we get 13 in our denominator. The only difference is when we did this one up here, we were multiplying by 1, so the numerator was easy. Now we just got to FOIL out the top, right? So 4 times 3 is 12. 4 times negative 2i is negative 8i. 5i times 3i is 15i. And then we get negative 10i squared. And then again, combining like terms. That negative 10i squared is the same thing as plus 10. 10 and 12 makes 22. And then I get a negative 8i and a positive 15i. So those combine to become 7i. And we would be done. Okay? So again, it's not a whole lot like you're really, truly dividing. It's more of just simplifying. Okay? Let's try another one here. Let's say we had something like this. 2 plus 6i, negative 3 minus I. Again, we just figure out the conjugate of the denominator. It's always the denominator because we're just trying to make that a real number. The conjugate would be negative 3 plus I. So whatever we do to the bottom, we do to the top. I like to do the denominator first because I think it's the easiest. Negative 3 times negative 3 would be positive 9. My middle terms are always going to cancel. I really don't even have to worry about it because I did that on purpose. And then I end up with negative I, positive I would be negative I squared, or the same thing as plus 1. So again, I'm going to get 10 in my denominator. Now all I have to do is FOIL out that top. So I get 2 times negative 3 is negative 6. 2 times I is 2i. 6i, negative 3i is negative 18i. And then I get negative 6i squared. This thing here is the same thing as positive 6. So now actually my real parts cancel, right? Negative 6, positive 6, those are gone. And all I have is this 2i, negative 18i is negative 16i. And actually this one I can reduce because if you can divide the both top and bottom by the same number, you can reduce it just like any other fraction. This one we can reduce both of those by 2, so I get negative 8i over 5 would again be my final answer there. Okay? Just as another side note here, another thing we can do here, now that we're dealing with imaginary numbers, is we can solve some more quadratics, right? You try to factor, it doesn't work. So we go to our quadratic formula. Remember our quadratic formula, negative b plus and minus the square root, b squared minus 4ac all over 2a. And then we plug in. So negative of b would be positive 2 plus and minus the square root of b squared, which would be positive 4, negative 2 squared, minus 4 times a, which is 1, times c, which is 5, all over 2 times 1. So I get 2 plus and minus the square root of, this would be 4 minus 20, or negative 16, all over 2. Now, before, if we saw that, we'd just say no solution, and actually there's no real solution. There are imaginary solutions, because this would be the same thing as 2 plus and minus 4i over 2. And yes, this, because both of these numbers can be divided by 2, that is the same thing as 1 plus and minus 2i. So that would be our solutions to those, okay? I'll put a picture of the problems on the board at the bottom. Give it a try. Let me know how it works out, okay? I will talk to you guys later.